All right, so section 5.2, this is on the fundamental theorem of calculus. And so we're going to talk more about this concept of the antiderivative and the integral and how that relates to the area under the curve, like what was in the last section. So as you might imagine, an antiderivative is just the opposite of the derivative. So if we start with a function and instead of taking the derivative, we go the other way, that would be called the antiderivative. And that's also the same idea as the what's called the integral. So when we talk about the integral, we are talking about the area under a curve, or we could just be talking about the general antiderivative. So the fundamental theorem of calculus says if a function is continuous on an interval, a closed interval a to b, antiderivative or the integral from a to b of little f of x, we'll call it capital F of x. We'll let capital F of x be the antiderivative of f of x, and f of b, capital F of b minus f of a is going to be that definite integral. And so that will give us the area under this little f of x curve. All right, so this section is a little bit more abstract in that we're not really looking at applications right now for this one. We're just going to take some antiderivatives and plug in values possibly, or just get a general antiderivative as the case may be. So this first one is evaluate the integral from 0 to 1 of x squared dx. And so that's normally the way you would read this, the integral from, and then you start with the bottom number, go up to the top. So it's from 0 to 1 of the function. All right. So as we know from derivatives, when we take the derivative of a polynomial or just a power function, as the case may be, if you were to take the derivative of this, you bring the exponent down and subtract 1 from the exponent. So the derivative of x squared, as you know, is 2x. So if we want to go the other way, it would make sense that the exponent of the antiderivative would be 1 more than what we started instead of 1 less. So it's going to be 3x, or sorry, not 3x, x to the third. But the derivative of x to the third is not x cubed. So how do we fix the derivative of x cubed is 3x squared, not x squared. And so what we need to do is divide by the 3. So the antiderivative of x squared is going to be x cubed over 3. And you can check this. You can always check these antiderivatives by just taking the derivative of your answer. So if we take the derivative of this, we should get x squared. And we do. So multiply the exponent by the coefficient, which is 1/3. 3 times 1/3 is 1. Subtract 1 from the exponent, which is 2. So the derivative of this is indeed x squared. And then according to the fundamental theorem of calculus, we're going to plug in the upper limit, plug in the lower limit, and then get the difference. So we are going to plug in 1. So 1 cubed over 3. And then we'll subtract and plug in the lower limit, which is 0. And of course, this is just going to give us 1/3. And that is it. So we'll talk about formulas for this, but that's the general idea. If you're looking at a function and you want to get the antiderivative, think how you would get the derivative in a simple case like this one. How would you get the derivative and then do the opposite? So you subtract 1 from the exponent, we're going to add 1 to the exponent. You multiply by the original, we're going to divide by the new one instead of multiplying by the original. So we're essentially doing the opposite. Now, it's not always that simple. The more complicated the function is, the more complicated it is to get the antiderivative. But there are methods for doing that, which we'll talk about a couple of them in this course as we go along. All right, so now, number 2, find the most general antiderivative of the following functions. Now, when it says general antiderivative, we do not have limits. So like number 1 was the limits of the integration were 0 to 1. when we talk about the general antiderivative, we don't have limits. So it's just a general antiderivative. Um, and so we'll just call this capital G of t. The derivative of capital G would be little g. And so we're going to take the antiderivative of this, same way as we did the last one. We're going to add 1 to the exponent instead of subtracting 1. And then we're going to divide by the new exponent. And now, with the general antiderivative, we always have to add a constant to this. Now, why do we have to do that? Well, the derivative of a constant is 0. And so that doesn't change the derivative. So if we take the derivative of this, the derivative of that is 2 to the 4th, as it should be. The derivative of the constant is 0. So you always have to add that. And all the constant does to the graph of the function is move it vertically. So you're not changing the slope at all. And you're not changing the area under the curve by doing that. And we could show, and maybe we'll do that in a minute. But if you have a definite integral that we want to do, you can put the c in. It's not going to change what the area is. So when we plug in the limits, it doesn't change. So we'll talk about that when we get there. All right, so b is y equals 1 over x. So we could rewrite this as x to the negative 1. Now, the problem here is if we do the rule that we talked about for this one and the previous one, add 1 to the exponent for this one, and we get 0. And then, of course, we cannot divide by 0, so we're dividing by the new exponent. We can't divide by 0. So that doesn't work. But do you know any functions whose derivative is 1 over x? Hopefully you do. The derivative of ln of x is 1 over x. So the antiderivative of 1 over x is, and let's call it capital Y. Just keep going with that. Capital Y would be the antiderivative and ln of x plus c. Now, one thing, as long as we're getting a general antiderivative, what's the domain of this function? The domain of this function is all real numbers except 0. What's the domain of this one? The domain of an ln, a logarithm function, is all positive numbers. So x cannot be negative. So whenever you need to make sure x is not negative, we're just going to put the absolute value there. So the antiderivative of 1 over x is just ln absolute value of x and then plus constant. All right, and then probably for c, you can probably figure this out based on part A on this one and then number 1. To get the antiderivative, like I've alluded to, we are just going to add 1 to the exponent and then divide by that new exponent. And I should probably say n is not negative 1. Yeah, n is not negative 1, because then if n is negative 1, then we're in this situation. So typo there. All right, so, and then of course you have the plus c. All right, so that's the basic type. Obviously, you should probably be very, very comfortable doing those. All right, so we'll stop this one here and then look at other more complex examples as we go.